How do you tell one bathroom full of statisticians from another? Check the p-value. Get it? Haha. So we are going to be using p-values to compare means today. And this is going to feel kind of repetitive, which is a good thing. So our initial evidence, we're looking at the smokers again when we did the confidence intervals. So we have 26 smokers, mean heart rate of 80 beats per minute, standard deviation of 5. 32 that have 74 and a standard deviation of 6. And we gave you the conditions already. They're roughly symmetric and had no outliers. So our initial evidence is the difference, that it is positive. It's 6 beats per minute. So you could almost make a small argument for that. But that's a beginner statistician argument. This value right here, again, is called our point estimate. So when we're performing a two-sample t-test, it's going to look a lot like a two-proportion z-test, except now we're using means, and our null is always that the difference is 0, that there's no real difference between them. And you can also write it that the two means are equal. So either way will work. On the calculator, it'll probably be more like the right. When you tend to calculate a t-value itself, you tend to use the one on the left. All right. And then the alternate form of the hypothesis can take several values. It could be not equal to 0 if it's a two-tailed test, greater than 0, or less than 0. So for our smokers, we're going to say that the null hypothesis is that the mean heart rates are not different at all, that the difference is 0. And our alternate is we suspect that smokers are going to have a higher heart rate because they're not quite as healthy. And remember to provide context, where mu of S is the average heart rate for the population of smokers, and mu of S is the average heart rate for the population of non-smokers. And we could probably argue, I think this was in a gym or something, and provide a little bit more context there. Now, remember, you've seen this before, this isn't the only possible value, because so we need to consider the sampling distribution. When subtracting two independent random variables that have approximately normal distribution, the difference will also have a normal distribution, or approximately normal. So these are the conditions, again, the same ones. The large normal, that the sample size is greater than or equal to 30. Luckily, if we have more than 30 in our sample, even if the original population is not normal, the distribution of means will be approximately normal. And then, of course, the random. Again, we want a well-designed random sample or randomized experiment. If they tell you it's representative, that's good enough. And the 10%, which we don't run into too often, especially not on experiments, but we do tend to do it more when we're doing surveys. Check that if we're doing a sample. All right, so we're just going to confirm again the conditions. As we said, it is stated that it's random. And the data, it's given that the data is roughly symmetric and there are no outliers. So they kind of gave us that one. So now that we're going to do that, let's get to the do part, the calculation. And we always need to do a standard error because we don't have the standard deviation. And before, when we did this, we actually used what was called a pooled proportion. Now, this assumes that the proportions are equal. And if the proportion is known, then we know the standard deviation. But for means, there's no real relationship between the average and the standard deviation. We'd have to assume the variances are equal, all right? And it might be appropriate in a comparative experiment where you said, oh, let's take a set of twins, or maybe you'd say, okay, we're going to do a before, after. You could possibly do it there, all right? Because you're starting with the same population variance. But honestly, that's so rare. Don't ever pool for a t-test. All right, so remember when using a list of data, you can always use one-var stats to get your standard error. And for random variables, this is hopefully starting to become familiar. The variance of the difference of two variables is just the sum of the two variances right there. So when I square that, I get these. And so when I want to find the standard error, I could say 1, 2, I did X and Y. Basically, this is the formula, which looks suspiciously like your math chart. So that is on your math chart in the back. You will have that as a resource. So, accounting for the differences in comparing means, remember, we're going to need a standardized test statistic. So it's going to be our statistic minus our parameter. Our point estimate is our statistic, and that's the difference in the two means. And I'm going to subtract 0 because we're assuming that the parameter is 0. That's our null hypothesis. Then we have the standard deviation of the statistic, and we just showed you that formula on the previous slide. And then we're eventually going to need this degrees of freedom. So we're going to calculate the degrees of freedom for each individual sample and use one that is smaller if we're using the comparative method. Although we hardly ever use that, honestly, we tend to use the calculator because it will give us a nice, it'll give you a higher degree of freedom, and which allows you to be a little more precise on your p-values. And also when you're doing confidence intervals, it allows you a tighter confidence interval. So conclude is the same. Basically, we're writing because our p-value is something. It's either greater than 0.05 or less than 0.05. If it's greater, we fail to reject. If it's less than, we reject. By the way, it could be some other alpha like 0.02, 0.01. Just use whatever's given to you. There's insufficient if it's greater than 0.05 evidence. And if it's less than 0.05, there's sufficient evidence that the true mean of whatever our context is the alternate hypothesis. And remember, avoid the words like prove and accept. Those are big no-nos that will go move an E to a P. All right, let's complete do and conclude for our pulse rates. And so we have, I went ahead and put our values right here from before. We're going to calculate our standard error, which is the same as what we got before. The only new thing is we're doing a t-score here. So there's my point estimate and from my statistic. And then I subtract my parameter that the difference is 0, and I put this 1.44 underneath, and I get 4.15. Now I will need to use a calculator to get the p-value using this with just the statistics. Now I could have done this with TCDF and used 25 as my degrees of freedom, but you're going to see if I use the calculator, I get a much higher degrees of freedom. So my conclusion is because the p-value is so small, the observed difference is unlikely to be just sampling error. Now this is a little bit more wordy conclusion than usual, and that's fine. We reject the null because p is low, all right? We have strong evidence of a difference in mean pulse rates for both smokers and non-smokers, all right? Now we're going to show you how to do this on the calculator. First, you're going to press stat and test like we've been doing, and you're going to scroll over to this 2SAMP t-test over here. Select stats when you get this input menu. X1 is your average for your sample. S of X1 is your standard error for that sample. N1 is sample size. Mu1 is select the one that matches your alternate. So if it's equal, less than, or greater than, just make sure it's there. Always select no here, okay? And then scroll to calculate and press enter, and you'll get an output like this. Here you can see your p-value is quite low. And there's your t, and they also give you the degrees of freedom right there. Now for data, make sure your data is already entered in a list. And for list 1, so this is the prompt you get when you select data instead of stats. You'll put list 1 and list 2. Frequency should be 1 unless you actually do have a frequency list, which is pretty rare. Make sure that this line matches your alternate hypothesis, just like before. We're still sticking with pooled, and then we come down to this blacked out area for me, which says calculate, and then you press enter, and it will give you the results. Now we're going to revisit our pizza example from the previous lesson, but we're going to do a hypothesis test instead of a confidence interval. So first of all, our state is our two hypotheses. One is that the means are the same for both brands of pizza, of fat content. Remember, that's what we're looking here. And our alternate is, it just says, is there a difference? Not is one higher or lower. So we're going to use the two-tailed test. So we're going to have not equal to 0 instead of greater than or less than. Always provide your context. And here I tightened it up using the magical word respectively. So where mu of D and mu of PJ are the average fat content for pizzas from brand D and brand PJ respectively. So if your hands are tired, that's a good way to shorten up these difference context things. Our procedure is a 2-sample t-test. Conditions, random. Again, we're going to have to assume that it's representative. There's no mention. There's no reason to think that they would be different, but you never know. Maybe they pulled out the extra skim cheese when they were being sampled. Nearly normal conditions, we basically have our plots from before. Both are roughly unimodal and symmetric, so this will work. Now let's go ahead and do our calculations. Well, first of all, I went ahead and entered the data in a list, and I'm going to show you first what I got in one var stats for both of them. And I could go and calculate the standard error for the sample, and I could go ahead and calculate the t-score. And this is what I would get for the p-value from the calculator. But as we saw earlier, it's much easier to just go ahead and have the data in a list. Go to your test like we said before. Scroll down to 2-samp t-test. Make sure you're in data. You got list 1 and list 2. Frequencies are 1, and we're saying not equals 2, and no unpooled, and hit calculate, and you'll see you get the values we have here. Now I can also go back and go to tests and run the 2-samp t-test again, and instead of doing calculate, you always have this option. You can do draw, and you will get a drawing of a nice normal distribution. Now this one's going to be a little less interesting because the p-value is so small that you won't be able to see the shading on the graph. But you can see there's the t-score and a p-value on here. They said, oh, it's just 0. All right, since the p-value is very low, practically 0, we reject the null hypothesis. There is strong evidence to suggest that the 2 pizza brands have different mean saturated fat content. In fact, if you want to add a conclusion, brand B appears to have more saturated fat on average than brand PJ.